A differential equation looks intimidating on paper, but here is what it actually says. At every point, it hands you an arrow. The arrow says, if you are here, this is the direction you move next, and this is how steeply. Draw that arrow everywhere at once, and the equation stops being a formula. It becomes a field you can look at.
So where are the solutions?
Already on the screen. Drop a point anywhere and let it follow the arrows, always turning to match the arrow under its feet. The path it traces is a solution. Drop it somewhere else and you get another one. No algebra happened. We read the answers straight off the picture. The interesting equations in physics have a second derivative in them, an acceleration. That sounds like a complication, but there is a move that tames every one of them, and it takes 30 seconds. To know what a swinging or vibrating thing does next, you need exactly two numbers: where it is and how fast it is moving. Position and velocity. That pair is the complete state of the system. So give each number its own axis. Position across, velocity up. Now one single point on this plane is a complete snapshot. It tells you where the system is and how fast it is going, all at once. Acceleration has not disappeared. Velocity tells us how position changes, and the original equation tells us how velocity changes. Put those two rates together, and they make one arrow for the pair.
So the trick from the last picture still works.
Exactly. We will unpack that conversion next. For now, it means the equation can paint an arrow everywhere. This plane is called the phase plane, and it is where the rest of this series lives. Our first system is a mass on a spring, and it earns its place by being honest. Its rule is simple. The further you stretch it, the harder it pulls back in exact proportion. Paint that rule's arrows on the phase plane, and they swirl around the center. Follow them from any starting point, and the path closes into a perfect ellipse. Read the loop like a sentence. The path comes back to where it started, so the motion repeats forever, the same oscillation every time around. A bigger loop is a bigger swing. Stretch the spring further at the start, and you ride a larger ellipse.
And we can trust this picture.
Completely. The spring is the one system in this series we can also solve exactly with pencil and paper, and the formula agrees with the picture. That is the spring's job here. It is the case where we can check our tools against the truth. Now the star of the series, the pendulum. Its rule is almost as short as the spring's. Gravity pulls it back toward hanging straight down, harder at some angles than others. But that small difference has a famous consequence. There is no formula for the pendulum's motion, not a hard one. None. Generations of the standard course dodge this by pretending small swings, which quietly turns the pendulum back into a spring. We will not pretend, we will just draw the arrows. And the picture that appears is beautiful. Near the bottom, closed loops and eye shape. Those are ordinary swings back and forth. Above them, wavy paths that never close. The pendulum going over the top, around and around. And between the two, a single sharp boundary curve separating swinging from spinning.
The one glance tells me whether it swings or spins.
Exactly. The equation nobody can solve just told us everything it does. Same tool as the spring, wildly richer picture, and still zero algebra. One more reading skill, and you can skim any of these pictures like a headline. Look for the points where the arrows vanish, the places the system can rest. The pendulum has two. Hanging straight down, the arrows nearby circle around it. Nudge the pendulum and it stays close, orbiting the rest point. That rest is stable. Balance straight up, the arrows nearby flee. The slightest nudge and the pendulum runs away from it. That rest is unstable. Rest points and their stability. That is the long-run behavior of the whole system, read at a glance. Notice what we never did. We never solved anything. We drew what the equation says, direction and steepness at every point, and the behavior was simply there to see. Oscillation, rotation, rest, stability. But a picture will not tell you where the pendulum is after exactly 10 seconds. For that, we compute. And before the computing comes one small move with enormous reach. Next time, every equation in physics tamed into the same shape.